Hi, and welcome to week 4 of K-Club. Let's get down to business. So today's topics will be the approach section, so that's the last section of the research strategy, and then action items, which is essentially to do your homework by writing an approach section. So let's get back to the K application section. So we've covered specific aims and NIH biosketches, and we've covered significance and innovation of the research strategy. So we're just going to finish up with approach today. So again, the approach is like a method section for a manuscript. You're explaining study design methods and statistical analyses to accomplish each of your specific aims. So we've already generated hypotheses in the significance section, but in the approach section, you're going to talk about the design of your experiment and what you expect to happen, the procedure of performing your experiment and analyzing your data, and then how you will draw conclusions, accepting or rejecting your hypotheses. So this should be the longest section in your research strategy. And you want to separate these into K99 and R00 research design subsections, and then within each address an overview, participants, assessments, power analyses for each aim, statistical analyses for each aim, potential sources of biological variation, expected outcomes, potential problems and alternative strategies, timeline and benchmarks for success, and future directions. So that is why we are covering approach in a separate week, because there's a lot to go over. Overview. So are you collecting data or doing secondary data analysis? Is this a pilot study to test feasibility of a new task or intervention? Are your data cross-sectional or longitudinal? Is your project focusing on between subjects, within subjects effects, or both? If they're between subjects, what groups or conditions will be involved? If within subjects, what conditions and/or time points? And if you have multiple time points or conditions and the procedure differs for each time point and condition, then say that in this overview section. In the assessment section, you can create subheadings to address each time point and condition. Next section, participants. How will they be recruited? If you have multiple groups, how will they be assigned or how will they be defined? How many per group and what is the age range? List inclusion and exclusion criteria and what assessments are needed to determine whether someone is eligible or not. Will they be screened for eligibility via phone or in person? Will they be asked to give oral during phone screening if applicable, and written in-person consent to participate, or one or the other? It's important to note that we haven't gone into creating your K99 and R00 budgets yet, but you need to start thinking about money now. So for the K99 phase, you get $20K per year for research, which is not a lot of money. You can't collect a ton of new data here, especially when factoring subject payment into the equation, or pay too much for fMRI scan time. You also can't buy a ton of new equipment or pay too much for any analysis services. Be mindful of this when designing your approach. So again, K99 phase, secondary data analysis, if that's an opportunity for you, I recommend taking it. For the R00 phase, you get up to $249K for everything, including research and salary. So you have a lot more money to work with in this phase for research. So this part of your application allows you to be more expansive in your approach during the R00 phase. After participants, the next section is power analysis. So let's do a little tutorial on power now to refresh our memory from statistics. And here we go. So for significance testing, you have your null hypothesis that the groups and conditions do not differ, and the alternative hypothesis that your groups and conditions differ in some way. So statistical power is the sensitivity of a statistical test and the probability that it will correctly reject the null hypothesis when it is false. So power is dependent on three things: sample size, effect size, and your alpha p-level value. So the larger the sample size, the lower the sampling error, making it easier to detect an effect. So typically, study design between versus within subjects affects sample size. So if you're doing within subjects design, and you have the same number of subjects as you would for a between subjects design, the within subjects design is going to give you more power. Effect size. So larger magnitude effects are more easily detected than smaller ones. And alpha level. So the lower the P level, the less power you have to detect an effect. So with an alpha P is less than 0.05 versus an alpha less than P is 0.01, you have less power to detect something at 0.01 than 0.05. So given any three of these, power, effect size, sample size, and alpha, we can find the fourth. And that's what you are going to need to do to ensure that you have a big enough sample size to detect what effects that you are hypothesizing you'll be able to see. Okay, so let's go through a bit more of an example. So here we have a box with hypothesis testing outcomes. Up top we have reality, and on the y-axis we have research. So the first box highlighted is that in reality the null hypothesis is true, and in research we also find that the null hypothesis is true, so there's no group differences. We have a match. And this is reflected by 1 minus alpha, which is typically set at P is less than 0.05. So at 95 out of 100 times, we retain the null, and we should. Typically, this isn't what we were hoping would happen, though, retaining the null hypothesis. So if you wrote your whole K99 R00 on retaining the null, I'm not super confident it's going to get funded. So yeah, null effects, probably no paper in Science. Let's look at another example. So in reality, the alternative hypothesis is true. So your groups or conditions differ. And in your research, it also shows that they differ. We have another match. And this is considered 1 minus beta. And beta is typically set at 0.20. So that means 80% or 80 out of 100 times we reject the null, and we should. Yes, we typically want to be able to reject the null and go with the alternative, and that is what our K99 and R00 hypotheses will be testing. Nicolas Cage is stoked. Okay, now let's get to the other two problematic times. So in reality, the null is true, but in our statistics, we reject the null, and that is considered a type 1 error. So there's a mismatch. So alpha is typically P less than 0.05, so 5 out of 100 times we reject the null, and we shouldn't. Again, type 1 error. Example, type 1 error, telling a man he's pregnant when that doesn't happen. You don't want your results to be as a result of type 1 error. What about type 2 error, where the alternative hypothesis in reality is true, but you fail to reject the null in your stats? So that's a mismatch. The beta is typically at 0.20, 20 out of 100 times we retain the null, and we shouldn't. And another example of type 2 error is telling obviously pregnant woman she's not pregnant. You don't want type 2 error inflation driving your results. So in terms of determining statistical power, typically power is set at 0.80, which means that the probability of a type 2 error is set at 0.20, and the probability of a type 1 error is set at 0.05 or less. So you are essentially walking the tightrope between a type 1 error and a type 2 error, and you want to balance the likelihood of both of those things when you are doing your power calculations. Let's talk about the importance of effect size. So null significance hypothesis testing reflects the reliability of an effect. So how often we expect it to happen. With P less than 0.05, that's less than 5 out of 100 times under the null hypothesis. So effect size is the magnitude of the effect, so how big it is. So we can always reach statistical significance if there is a large enough sample size, unless the effect size in reality is truly zero. So even a large effect may not be statistically significant if the sample size is too small. This is tricky. There are different measures of effect size and different interpretations based on the particular metric. So when you're looking for effect sizes in the literature to base the effect size you plan to achieve for your grant, make sure you understand the different interpretations. So one interpretation of effect size is the difference between two variables' mean values as a certain number of units. So Cohen's D, Glass's delta, Hedges G, and Pearson's correlation R, those effect sizes all reflect this difference between two variables' mean values in a certain number of units. There's another effect size metric reflecting the proportion of variance shared between two variables. R squared, eta squared, and partial eta squared, all effect sizes are all defined as a proportion of variance shared. All right, now we're going to tackle power analysis for each aim. So the effect size you want to obtain will be based on previous literature that tested something similar. Effect sizes reported in papers could be eta squared, partial eta squared, Pearson's, Cohen's D, Hedges G, or R squared. Even if the paper did not report an effect size, you can calculate it if the paper reports the means and standard deviations per group. So you can't use the excuse, oh, well, they didn't report effect size in their paper, therefore I don't need to do a power analysis to determine what sample size I need to get a certain effect. Nope, that doesn't cut it. Explain what software, so there's software called G-Power or RStudio that you can use to figure out your sample size, given alpha equals 0.05, power equals 0.80, and the effect size you want to get. So for example, Cohen's D equals 0.5, that's a medium effect size. So there are plenty of online calculators you can use to get this information. So for power analysis for each aim, this section is very important for a grant application. Ask your primary mentor and mentorship team for help if you get stuck. So at Library, we have G-Power that can be installed on your computer, and there are G-Power manuals and tutorials online. You can just Google them. And below are some links to help you calculate power. Yes. So again, you want to show the reviewers that you did your homework and figured out the effect size you are planning to obtain, that you have enough subjects, you have enough power to detect those effects, to replicate them, extend them, whatever you are planning to do. Now let's talk about statistical analysis for each aim. So what statistics program will you use to analyze your data? You're going to restate each hypothesis from your specific aims page. You're going to explain what test you will use to evaluate each hypothesis. So an example would be mixed ANOVA with group, depressed versus control as the between subjects variable, condition as the within subjects variable. So say I was doing a monetary incentive delay task and I had no win, small win, and large win conditions. And 3, striatum activation as the dependent variable. So in this case, I'm recording fMRI during the task. I pick a striatum region of interest, and that is my dependent variable. You want to be as clear as possible as to what effect you're looking for, because you want to gain reviewers' confidence that you understand statistics and know how to analyze your data correctly. So what is the outcome of interest? Is it a group by condition interaction? Is it something else? Is it a main effective group? In addition to test statistics, so if you are doing an ANOVA, you're going to report the F, degrees of freedom, and p-values. What other statistics will you report? Be clear about this. So effect sizes, say what measure you will use, Cohen's D, Pearson's R, etc. Reviewers like to see 95% confidence intervals. And explain in what context you will do post hoc tests. So say you are looking for a group by condition interaction. If that overall ANOVA group by condition interaction is less than p.05, then you will do X post hoc tests to determine group differences. How will you correct for family-wise error and multiple comparisons? So you're rarely doing just one test per aim. I mean, you can, but reviewers are going to want to see that you're thinking about inflation of type 1 error for running too many tests. Next up, potential sources of biological variation. So here's where you need to justify what age range you're using for your study, whether or not you'll have enough statistical power to compare your results between males and females for biological sex, and whether or not you'll have enough statistical power to compare your results between races and ethnicities, and if so, which ones. So for example, with certain library data sets, we have enough statistical power to compare males and females and say Caucasians and Native Americans, but we may not have power to detect differences between Blacks and Asians due to the makeup of Tulsa, Oklahoma. So then you want to address any other biological differences that could be relevant to your study. So with peripheral blood biomarkers, analyses typically include body mass index. So we might want to discuss the range of body mass index scores that we have, showing that we have enough variability to include that in our analyses. Expected outcomes. So what do you expect to happen with your grant if everything goes well, if life is sunshine and rainbows? This is the ideal scenario if everything works out as you hypothesized. So you can take this from specific aims and expand on it, but you want 2 sentences explaining the payoff reviewers can expect to get if they vote to recommend funding for your project. There should be at least one expected outcome for each aim, and they should collectively relate to your overall grant objective outlined in specific aims. Now we're going to get to the flip side of expected outcomes that are all positive, but this is for when things go wrong. So potential problems and alternative strategies. Think of problems you might encounter with your study and steps you will take to overcome these problems. So let's go through some examples. Say you have issues with recruitment, so problems with your recruitment sites, there's too many people being excluded due to your inclusion and exclusion criteria, high participant dropout rates, maybe they don't like your real-time fMRI neurofeedback protocol, potential adverse or unexpected events, say you did an experiment using stimuli reflecting disgust and people actually got sick because your pictures were so gross. What are you going to do about that? If you're testing feasibility of a task or intervention and it doesn't end up working, how will you use this knowledge to change your task or intervention? So brainstorm some ideas, talk to your primary mentor about this. So you've outlined essentially your study design. Now you're going to convince the reviewers that you thought through and planned when you're going to complete each step of this research process, when you're going to complete data collection, data analysis, pre-processing, statistical analysis, and writing up results. So for K99R00, you're creating a 5-year research timeline. So outline the number of subjects per month for recruitment if you're collecting new data. If you have a longitudinal design, how many subjects will be completing sessions every year? When does data preprocessing and analysis happen? If you're doing secondary data analysis for your entire K99R00 project, you will need to be able to show why you need 5 years to analyze the data and write up the results. Last but not least, future directions. So where are the outcomes of this project expected to lead? How these outcomes separate your research from that of your primary mentor. So a huge thing with K99s and R00s is research independence. So how what you learn from this project be able to have you go off in your own direction. You might be wondering, how am I going to fit this approach section, the significance and innovation sections into a 6-page document? It really does take magic. So right now, don't worry about the page limit. Your mentorship team can help in cutting words later. There's lots of page limits for K99R00 sections. it's fine to wait until later to cut stuff down. So your homework for this week is to revise your significance and innovation sections based on your primary mentor feedback, and write a draft of your approach and get feedback from your primary mentor. And then you will be done with your draft of the research strategy. Good luck.